Hello and welcome to a Safer Sim webinar. Today we have Boris Claros from Wisconsin, University of Wisconsin at Madison and the TOPS Lab. Boris, please take the floor.
Okay, thank you very much. So yeah, my name is Boris Claros. I'm a research scientist in the TOPS lab at the University of Wisconsin Madison. And today I'll be presenting two research projects that we conducted as part of the Safer Sim consortium. And one of the projects is about bicycle naturalistic data. And the other project is about field-based evaluation of left turn behavior variations. So to start with, we're going to start with the naturalistic biking study. So the objective of this project was basically to put together a instrumented bicycle and collect data that could serve for the basis of the development of simulation environments, particularly in the behavior of passing maneuvers with bicyclists on rural roadways. So to give a little bit of background about this project, uh, bicycling has increased in popularity in recent years, especially after the pandemic. And we know that it has become a way of recreational activities and also for commuting purposes. Some of the measures that are usually used to measure safety or to evaluate safety are the lateral passing distance. And in the US, 3 feet is considered a safe distance to pass bicyclists on the road. I should mention that there are other countries in which there is a differentiation of urban and rural regions in which the threshold is different. It's not specific to 3 feet. And this could be based also on the speed limit or the type of or the functional class of the roadway. So yeah, like I mentioned, in other countries, actually there is a differentiation of the thresholds that are provided for passing a bicyclist on the side of the road. And like I mentioned as well, there is very limited research that is specifically related to rural areas. Most of the research that is available and also from naturalistic studies is in urban environments. So what we wanted to focus on mainly was, how these, passing maneuvers of vehicles occur on high-speed roadways or in rural roadways, which, are not, there isn't much information about. So the objectives, like I mentioned, are to instrument a bicycle specifically for naturalistic data collection and to measure the lateral distance when vehicles pass the bicyclist on a specific, high-speed rural roadway with two lanes. And we wanted to evaluate, for purposes of replication and use in other environments, was to measure and model the distribution of these movements, the vehicle bicycle lateral movements, and evaluate different factors that play a role in these passing maneuvers. So we focused on the opposing traffic, when a vehicle is passing a bicyclist and whether there is an opposing vehicle present in the opposing, lane. Also, we focused on whether, the passing vehicle type, whether these were, passenger vehicles or, heavy vehicles or semi trucks. We also focused on the pavement and marking condition. We were fortunate that during the data collection that we conducted, uh, the roadway in which we were collecting the data was, upgraded or repaved, in which, a new pavement was implemented and the pavement marking was also implemented. So we had a before and after comparison for that condition. We also had the evaluation of whether there is an effect when a vehicle, a passing vehicle is leading a platoon or is following a leader in the platoon. So we also did that comparison. So, so when we collected the data, uh, some of the sensors that we instrumented for the bicycle were video cameras. These were GoPro cameras that had the capacity to record around 1 hour and 45 minutes, and we had four aiming at different angles of the bicycle, so we could collect a 360 coverage around the bicyclists. Then we had a geolocation device, which is part of the bicycle computer that you can see it here in the front of the bicycle, and that basically you know uh, collects most of the data from the sensors, including the rider heart rate, the speed, and the cadence of the bicyclist. And then we had another sensor that we developed in the lab, which is this cone shape uh, ultrasonic sensor, which measures the lateral distance from an object passing the bicyclist. So and we develop and assemble all these sensors into the bike, so we could collect data many times. So we were on the road several times. At one part of the study, we collected approximately 2,000 miles of data in with different conditions. So let me go ahead and show you a little bit more about the details of the sensor that we developed. So we developed 3D models to specifically design a sensor casing and a compact design in which we were able to kind of hide the sensor and not make it too visible. And we developed all these in a 3D model so we could mount it on a bicycle and have it all according to the specs that we would like to have. And we can see some pictures here of prototyping, how we you build a little LCD screen with a data logger in which we have an SD card where the data was going to be stored, and all the assembly and power source. For instance, we had a battery that was rechargeable, so we only need to connect the cable to recharge the battery, and we didn't need to remove the entire case or sensor from the bicycle. And the same with the SD card, we just had to remove it and put it back again to retrieve the data that we collected. And obviously we use 3D printing for the for this case. So let me go ahead. Yeah, so just an example, once we collected the data from the different sensors, the video, and all of that information, we needed to integrate everything into one video. So basically, we overlaid different sensors and video using, editing software. And this is an example how it looks. So I'll run the video so you can take a look at more or less what we have. So right now we have the bicyclist riding on the shoulder on a rural roadway. This is in Wisconsin. You can see a little bit of snow on the side of the road, and pretty soon you're gonna start seeing opposing traffic, and then you're gonna see a semi truck passing the bicyclist as well. So yeah, the semi truck is approaching, and you will see how is the interaction with the bicyclist. And for instance, you can see that the semi is slowing down a little bit because there's opposing traffic, and then the semi is moving over to the opposing lane to give room to the bicyclist. So yeah, so these are some of the interactions that have been measured, and you can see the sensor is measuring, what is the lateral distance every time that each of these vehicles are passing the bicyclist. And on the right, you can see specifically, what is the speed of the bicyclist, the cadence in which the bicyclist is pedaling, and even the heart rate in which, the bicyclist has at that point. So yeah, so these are, basically we process all the data, we have it in video, and then we extracted some of this information to determine, for instance, the vehicle type, whether the vehicle went over the center line or not. So different positions and all of that data was also collected. So we also, in addition to the naturalistic bicycle data collection, we also obtain a LiDAR sensor in which we use to do a more stationary data collection on the side of the road, specifically to map out some of the trajectories of vehicles. And here we can see an example that we collected that data and also kind of validated with video to see how those data points are collected from the LiDAR device and how we can use them to specifically map out the trajectory of vehicles or from the side of the road from a stationary location as well. And like I said, we basically synced the LiDAR device with the video just to validate some of these observations and how we can process these data points as trajectories. Uh, just as to show the overall results from the study that we conducted from the naturalistic section of the bicycle data collection. Like I mentioned before, that we focused on opposing traffic, we focused on vehicle type, we focused on what type of approach type was the vehicle passing, and then the pavement condition. And for all of these categories, we focused on, I think, on one of the most important factors when passing a bicyclist is whether there is the presence of opposing vehicles or opposing traffic, which restricts the space that a passing vehicle can provide to a bicyclist on the side of the road. So we can see here the different tests that we conducted to see if there are statistical, differences among these groups. And, I know this is showing a lot of numbers and a lot of p-values, but I'll go ahead and show you one by one each section so you can have a clearer view of what all of these comparisons are, at least the most relevant. So for instance, the opposing traffic, right? What are the distributions when there is opposing traffic and there isn't one? So we can see that, the mean distance from the bicyclist when there is a opposing traffic, it's 147. And when there isn't opposing traffic, like the diagram is showing, it's, is graded. These measurements are, I'm sorry, are in centimeters. They are not in feet specifically. They are in centimeters, uh, just to get a little bit more granularity from the sensor and easy, to process the data, as well. So that's one aspect that we have. The presence of opposing traffic is the main contributing factor to the lateral distance when passing a bicyclist on a rural roadway. Then we have another case in which it's the passenger vehicle and heavy vehicle. So we can see clearly that, heavier vehicles have, larger size, so they will be less likely to provide room to a bicyclist based on, also whether there is opposing traffic or not. So also, the dimensions of the vehicle play a role in the lateral distance when passing bicyclists. So we have another one, which is whether the follower vehicle or it's a leading vehicle. Although it's a smaller difference, we still believe that the following vehicles have less reaction time to see the bicyclist because the side of view of the following vehicle is obstructed by the vehicle in front, especially when the bicyclist is on the right side of the road. So there's still a significant difference between that, and that's what we were able to capture with the data that we collected. Also, I mentioned before that we did essentially a before and after. There was a significant difference between an old payment condition and a new condition that we were able to determine, and we think that that might be because the payment marking delineate exactly the dimensions or the projections or the locations of where the bicyclist is on the roadway, and that might play a role in how vehicles positions themselves when they pass a bicyclist on the road. And from all the results, from all these distributions that we have obtained, we have basically come up with a equation in which we can calculate the probability, basically, of vehicles that would pass the cyclist given a certain threshold. For instance, in this example, we have that, what would be the probability of vehicles on a roadway passing a bicyclist below 3.3 feet? And that probability can be calculated as a function of how many or how, what is the percentage of those maneuvers that will encounter opposing traffic. So we simplify the equation in a way that could be useful for practitioners to implement, determine, or basically as a function of how much opposing traffic there is on the roadway, particularly on a two-lane roadway. So that's what we did. The probability distribution that we implemented is a mixed probability distribution, which consists of combining two separate distributions into one, and that account for basically the percentage of opposing traffic from all the observations. And this is a little bit more of the example, just illustrating how that probability is estimated, right? We have two probability distributions, and the solid line is basically the mixed probability distribution, which we use to estimate the probability of, passing vehicles given, a certain thresholds. And then we basically normalize these equations that is a function only of the opposing traffic. So moving forward, the conclusions. So we found that there is a significant effect of opposing traffic, as I mentioned before. Heavy vehicles, also when vehicles are in a platoon, and also pavement condition play a significant role in the passing lateral distance. And we believe that even now, these results are aimed at contributing to simulation studies to basically model these passing behaviors that should replicate when actual drivers interact with bicyclists in a simulation. That should this should be as a baseline data to be replicated in a simulation scenario. And we're hoping that these parameters, these trajectories that we found, and this lateral distance could hopefully benefit, to develop scenarios with driving simulators. And that's something that we are currently working on. We have another project, which is an NCHRP project, that is looking into the effect of rumble strips in safety of bicyclists. And basically, we're going to be using these parameters for that particular case. Before I move on to the other section, I know we're probably going to have questions at the end. Is that correct, Don? Okay, so probably I'll move on to the next presentation. Okay, the next presentation, it's for another project that we had from also one of our students was involved in this study, which was to conduct an evaluation of left turning behavior, but the focus was specifically to conduct an evaluation at the individual driver level. So we wanted to see what is the behavior of a specific individual, because usually most studies on left turn critical gap or gap evaluation focused on an aggregate of the population, but not the individuals themselves, how their behavior changes according to different conditions. So this study more or less tried to focus on that. What is the variation within one individual? So one of the main elements for roadway analysis or traffic analysis, the roadway capacity, which is a constant concern when we're looking at the network. And one of the essential factors that is used in the calculation of capacity on a roadway is the saturation flow rate. And left turn maneuvers, specifically permissive left turn maneuvers, are among the most challenging to accommodate in a design. So the saturation flow rate, for instance, is the lowest with left turn maneuvers. So in this case, that's why we're trying to focus on left turn maneuvers for the design, or or evaluation of individual left turn maneuvers and what are their specific saturation flow rates. So I'll go over what the saturation flow rate is, and it's essentially calculated in the highway capacity manual. It's been used for many decades. So the saturation flow rate is calculated as a function of two fixed parameters, which are the critical headway and the follow-up headway. These two parameters have been developed in the 1970s from a couple of locations in Texas, and they were calculated as a fixed value from those populations that were collected back then. So we recently published a paper in which we specifically calculated new critical gap headways and follow-up headways. And also this study is was trying to look into that variation of critical gaps as well. So to explain a little bit more, what are these two parameters that are used for the calculation of the saturation flow rate? One is the critical headway, which is basically the lowest time between two vehicles in which a left turn vehicle can safely maneuver through, right? So that's basically what is the shortest gap that a vehicle can take. Then we have the follow-up headway. The follow-up headway is between the vehicle in front of the lead vehicle and the following vehicle that is trying to make a left turn. So the follow-up headway is calculated as an average in seconds, like between the leading left turn vehicle and then the actual following left turn vehicle, making a left turn maneuver in the same gap or in the same headway. So those are the two parameters. The critical headway in the highway capacity manual is a fixed value of 4.5 seconds. The follow-up headway also in the highway capacity manual is 2.5 seconds. And like I mentioned, those have been used for many decades. So the objective was to collect individual driver data, to perform an exploratory analysis to assess what are the data requirements to evaluate the data at the individual level. And the objective was to measure or to gather all this data to measure the differences of the varied headways that each of these individuals would encounter, and how are their conditions, or how they would react to these different, facing these different headways or different conditions. So what we did is we collected field data from a location here in Madison, Wisconsin. In the location was Regent Street and Randall Avenue. The data was collected during 2021 and 2022 during 17 days. And the period of analysis was specifically to 7 to 10 a.m., hoping to capture, regular commuters that were going to work. The idea was to capture these commuters multiple times, so we will have multiple observations for each of these individuals. That was the objective. So what we did is to identify who these commuters were. First, we needed to identify what are or who are these repeat commuters with this license plate. So what we did was we identify license plate for every observation, and then we could match them, as we move forward for the data in the different days. And once we identify, who were repeat commuters, we basically took timestamps of the video to determine, when they arrive at the stop bar, how many gaps they rejected, what gap they accepted, and basically we collected all this timestamp data to determine the gaps and what gaps were rejected and accepted. So overall, there were approximately 1,307 observations, but unfortunately, that's the aggregate of the data. But when we look at the individual data that was available, or the individual, for every individual, there were what were the number of observations that really narrowed down to just some of the individuals in this data set, right? So for instance, there were 50 or more vehicles that only observed had 5 or more observations. In the majority of these 50 observations, only, although they arrived at the intersections, they did not accepted or rejected any gap. So there were not enough traffic in opposing traffic for them to interact or look for a gap. So those were some of the limitations encountered. And unfortunately, there were only 8 individuals or 8 vehicles that had data, repeat data that we were able to use in this study, which was very limited from the 1,300 observations that we initially had. So with the limitations that we ran into, we first computed the aggregated critical gap from all the users, right? Not repeat. So, and we can see that the 4.2 and the 2.7 are very similar to the highway capacity manual I mentioned before. The highway capacity manual has 4.5 and 2.5. And unfortunately, we didn't have enough data to confidently calculate the individual critical gap of these 8 users at least for us, because the maximum likelihood method requires at least 25 or 30 observations for every individual to be able to estimate the critical gap headway. So in conclusion, although the objective was to estimate the critical and follow-up headway at the individual level, unfortunately, it was not possible because of the limitations we run into with the capacity to obtain more observations per individual, and we were not able to complete that part of the analysis. And I think this study emphasizes how difficult it is to capture individual level vehicle data that could help us estimate the critical gap at the individual level, and hopefully this could help some other researchers to assess more or less the effort required and the period of time that will be required to gather this type of data. Okay, I believe that's all I have. I think if there are any questions.
Thank you. Thank you. So while our attendees are welcome to unmute themselves or type in the chat, either way, if you have a comment or a question. In the meantime, about your bicycle study, and that your differences were shown in centimeters.
Yes.
This is not a hostile question. I'm actually curious. Did you feel like that was a meaningful difference in the distance from the bicycle for these different types of passing vehicles?
Yes.
Or was it still concerning? Go ahead.
Yeah, we think that these differences were meaningful, especially, for instance, the presence of opposing traffic. That it was, yeah, there are some that are very small differences, but we saw that the distribution was shifted although that the mean is close,
Mhm.
the distribution is shifted, so that will help us, help us determine whether there was a difference or not. So we tested whether the two distributions that we observed were different or not. So
Mm.
that's some of the tests that we conducted. Yeah.
Yep. Thank you for reiterating that. I
Yeah.
remember you said it. I just made a note.
Yeah.
Because while I'm not currently a bicyclist, I used to bicycle to work, and how people got is a little scary.
Yeah.
Yeah.
So, well, I've been presenting the naturalistic bicycle research in several places, I would say recently. And also we have experienced, an incident, for instance, I've been collecting the data. So I was collecting data in Michigan and I
Mhm.
was hit by a vehicle with the side view mirror of the vehicle. We
Mhm.
usually show that video, but because of, how short this presentation is,
Mhm.
I couldn't accommodate, but yeah. So we usually show that, to encourage, some of the drivers, hopefully to, provide some room to bicyclists when they encounter them on the road, because it is very difficult to see these situations as well. And also we've been working on an NCHR project, like I mentioned, and we're reviewing bicycle crashes on rural roadways from different states as well. And we've seen that unfortunately drivers don't see bicyclists on the road. It's very unfortunate that, it's either the roadway conditions, curvature, or lighting, or the sun, obstructing the view
Mhm.
of drivers. And
Yeah.
unfortunately, there are a lot of fatalities and high injury severity accidents on these roadways, especially
Yeah.
involving bicyclists.
Yeah. Because of what I do, I tend to look for bicyclists and motorcyclists, but you know, I'm in the safety field. And
Yeah,
so,
yeah.
um, but yeah, thank you very much. Do any of our other attendees have any questions or comments? Just unmute yourself if you feel comfortable with that, or type in the chat. Okay. Well, I don't see anybody typing, and I don't see anybody in the meetings. Boris, I want to thank you very much for two very nice presentations. And thank you for being part of Saferson. You have certainly added to the significance of our work as a consortium. I appreciate that.
Yeah, no,
So,
thank you very much. I'm happy to be presenting this
yeah.
research.
And with that, we will say goodbye. And if anyone would like to rewatch the video of of this presentation, we will go up on YouTube in the next 2 weeks. Thank you very much.
Yeah, thank
Bye-bye.
you. Bye.